In today's video, we're going to be discussing the mass-energy equivalence. After watching this video, you should be able to explain what this mass-energy equivalence is, explain what mass defect is, and then be able to begin to think about how you could apply Einstein's equation to various problems. Now, with that being said, I probably have mentioned it in class, and I'm going to mention it again right now. A lot of the things that we're talking about, especially in this chapter, is just, in my opinion, flat out weird. It's kind of hard to wrap your mind around some of the concepts that we're talking about. Earlier in physics, I realized the content was probably hard, but I felt like if you would kind of eventually start to get it, it sort of made sense. If you thought about it enough, it makes sense. I feel like this stuff, you think about it some more, and it still doesn't frankly make sense, in my opinion. Like every time I go through this lesson, it boggles my mind. So I just want to give you a heads up on that this is probably going to seem a little weird. You're probably going to say, like, what the heck is this? But bear with me. Try your best to get a grasp on it, and then we'll work on it more in class together. So here we go. Just a quick review from the last lesson. A nucleus contains positive protons and neutral neutrons. And we discussed this new force, the strong force, which is responsible for holding the protons together in the nucleus. Because remember, the protons do not want to be there. They're positively charged, and they're trying to push away from each other, but this strong force is the one responsible for holding it together. Okay, so keep that in mind. Just some quick history for you. In 1905, Albert Einstein had this great idea that an object's mass is actually a measure of how much energy that object contains. So prior to this revelation, basically, the law of conservation of mass and the law of conservation of energy were thought as kind of separate statements. You're either talking about energy or talking about mass. They don't go together. Einstein actually said, no, mass and energy basically are the same thing. They're interchangeable. Mass can become energy, and energy can become mass. Okay, and you probably actually know this formula because it's one of the most well-known scientific formulas probably on the planet. It is E equals mc squared. Basically, if you ever think about what these letters mean, Einstein's formula says that the E stands for energy, M stands for mass, and c squared is the speed of light in a vacuum squared. And I'm sorry, I'm missing an equal sign here, but it's supposed to E equals mc squared. Typically, when we're dealing with nuclear physics, the energy isn't measured in joules, which I know is a very standard unit, but it'd be such a small amount of joules that you'd be writing like these numbers with like decimal point 0.00000 and then some number. So instead, we measure in electron volts. The mass typically is measured in atomic mass units. So instead of kilograms, you use atomic mass units. Now you could use kilograms if you wanted to, but again, you remember one atomic mass unit is like 1 times 10 to the negative 27th kilograms, or something ridiculously small. So we don't use that. Instead, we use atomic mass units. The speed of light is still 3 times 10 to the 8th meters per second squared. So that's not changed, but just a heads up on the energy and the mass piece. If you think about things, if you were to plug the mass of a pickup truck in this M piece here and then multiply it by the speed of light squared, which is going to be a massive number, it is easily enough energy to power the United States for probably like a good few years. Now, I'm not certain I didn't do the calculations on that, but what we're saying is basically a small object could produce a tremendous amount of energy if you take that mass and convert it to energy. Now, something that just kind of boggles my mind, it also means that an object, if it can actually gain mass, it can become more massive if it gains energy. Okay, I mean, most of our physics problems we've ever dealt with, the mass just stays constant. If you have a 10 kilogram bowling ball, which is a massive bowling ball, but let's say you have a 10 kilogram bowling ball, it's going to still be 10 kilograms when the problem's done. Not anymore. Okay, that bowling ball actually could gain mass if it gains energy. Okay, so these are just kind of weird things. So here's the mass energy equivalence. Let me get into I got my mouse here. Basically, what it says is that the nucleus, if we have, let's say we have an atom with 2 protons and 1 neutron. I'll say neutron, proton, proton. Okay, those protons, they don't want to be together, right? We'll throw another neutron in. They don't want to be together, okay? But the strong force holds them together. And that strong force needs energy, and that's referred to as the binding energy. The binding energy to hold them together. This nucleus right here, we'll call this nucleus. This nucleus, let's say it has a mass of 1. Okay, 1U, 1 atomic mass unit. Believe it or not, if I were to separate these protons and these neutrons, I'm just going to put them up here. I'm sorry this isn't more organized, but here's a proton, here's a neutron. They're just like floating around in space or whatever. Okay? The mass of this clump of protons and neutrons just kind of floating around in space is actually more than the mass of this nucleus. The reason why is some of that mass is being used as energy to hold it together. That's that binding energy. Okay? So what that basically says is that this nucleus is less massive than these individual parts, these protons and neutrons by themselves. Okay, so take a moment to kind of mull that over. I have 2 protons and 2 neutrons here, 2 protons, 2 neutrons here. If the mass of this one is 1 atomic mass unit, the mass of this guy might be like 1.2 atomic mass units. I'm just making this up, but it would actually be a little bit more massive because there's no binding energy being used here. Okay, they're just free to do whatever they want. Okay, so think about that. Here we go. Mass defect. What is that? The mass defect basically is the difference between the sum of the masses of the individual nucleons and the actual mass. Okay. Now, if we go back to my example from the previous slide, remember I had 2 protons, 2 neutrons, and we said this was a mass of 1U. Okay. And now, and this is a nucleus here. I probably spelled that wrong, but whatever. There's a nucleus. Now, let's say I have a proton, neutron. They're just floating around freely, okay? And we said this had a mass of 1.2 U. The mass defect is the difference of this mass from that mass. It has a fancy sounding name, but basically I'm going to take 1.2 minus 1, or 1.0. And I would get a mass defect of 0.2 U. That's the mass defect, okay? It's the difference in the mass between the nucleus and the individual parts if they were just to be sitting on their own. Okay, and if you want a formula for calculating mass defect, it's basically a subtraction problem. Here it is in all its glory. The mass defect is equivalent to the mass of the protons plus the mass of the neutrons as separate entities minus the mass of the nucleus that you're talking about. Okay, and I set it up in this fashion because this number right here, whatever that is, will always be bigger than this number here. Okay, this one will be smaller. And the reason why is this one's going to have that binding energy. It needs that strong force to keep it together. All right. You can do it the other way around. If you flip this, you're going to get a negative number, which is just kind of funky. So I like positive numbers, and so that's why I put it in this order. The mass of the protons and the neutrons by themselves minus the mass of the nucleus put together. Okay. So, what can I do with that mass defect piece? Okay, if I can calculate the mass defect, what can I do? Well, basically, I can determine how much the binding energy is, how much binding energy is needed to hold that thing together. And so, to figure that out, basically, I determine the mass defect by using the formula in the previous slide. Whatever that mass defect is, so in our example, it was 0.2 U, I can plug that into the E equals mc squared equation. My m would now be 0.2. Times the speed of light squared, and the energy calculated will then be in electron volts, and that energy is basically the binding energy. Okay. Now, to solve some problems, there's going to be some useful numbers for you guys to know. In a nutshell, we'll practice this a lot in class, and a lot of these will probably be given to you, but I just thought I'd let you know this stuff. 1 U is equivalent to 931.5 mega electron volts over C squared. Okay, so it kind of turns out a lot of times you actually don't need to throw your mass defect into Einstein's equation. You instead can just use a shortcut where basically you figure out the atomic mass unit, the difference, and you multiply it by 931.5. But we'll deal with that more together. The mass of a proton is this big long number right here, 1.007276 U. And a lot of times, problems won't give you just the mass of a proton. Instead, they'll tell you the mass of one hydrogen nucleus. And the mass of one hydrogen nucleus is one proton plus mass of one hydrogen, and it's one proton and one electron. And if they give you that, then the mass is this number right here. Okay, notice it's a little bit bigger because you have now an electron mixed into it plus a proton. What also is just interesting to note is probably your entire life, they've told you that protons and neutrons have about the same mass. The truth of the matter is the neutron is actually a little bit more massive than the proton. Not a lot, but a little bit. And so because we're dealing with such small numbers here, we actually need to take that into account, the difference between the mass of a neutron and the mass of a proton. So you can no longer just assume they're the same. Instead, there is a small difference, and here's the mass of a neutron right here, 1.008665 U. Again, a lot of these numbers will be given to you. I wouldn't expect you to memorize these or any of that kind of stuff, but just so you're aware, they do exist. Okay. I don't know about you, but that's kind of a hard lesson to swallow. So I thought I'll have a quick recap slide just to kind of sum everything up that we've talked about. Okay. Basically, Einstein says that energy and mass are equivalent. So you can convert between energy and make it into mass. You can take mass and convert it into energy. They're all the same. Okay. Now you still can't destroy either of them. They just can transfer between mass and energy. The mass of a nucleus is less than the mass of its individual constituents. So what that basically means is when you start putting protons and neutrons together in a nucleus, all clumped together, that mass is going to be less than if you took those protons and neutrons and just laid them out on a table, okay, and just let them sit there. Okay, and the reason why it's less is because there needs to be that binding force to hold them together. Without that binding energy, binding energy. Without that binding energy, those protons would not want to stay there because they're positively charged. Okay. That difference in mass is known as the mass defect, and you can use it to calculate the binding energy by using Einstein's equation, E equals mc squared. That takes care of today's video. I will see you guys next time.